Good morning, everyone. I'm Sriharsha. I'm a senior engineer at Meta, and today I'm going to share a research that sits at the intersection of AI, immersive technology, and human learning. So, the title of this talk, "Enhancing Human Performance Through Real-Time AI Feedback and Adaptive Learning," captures what I believe is one of the most important opportunities in professional training today. So we have extraordinarily powerful technologies these days, right? So large language models that can simulate human conversation, virtual reality systems that create immersive experiences, and adaptive algorithms that personalize learning. But there is a bigger problem, here. So these technologies have largely developed in isolation. So what I'm presenting today is an integrated framework for next generation clinical training that is grounded in a systematic review of 165 studies that we have made and informed by patented system architecture that I have co-developed with one of my friends. So this isn't a speculative design, I would say. It's evidence-based integration. So by the end of this session, what you'll understand is the current fragmentation in AI-enabled training, why integration matters, and how a unified architectural approach can dramatically improve outcomes. So let's dive into it. So, what's the challenge? So, before we discuss the solutions, we need to understand the problem we are solving, right? So, think of this as a slide, as a diagnostic report. There are five critical barriers that are systematic review identified in modern clinical education. The first one is going to be the systematic fragmentation. So, this is perhaps the most surprising finding. We reviewed 165 studies on AI enabled clinical training systems. 67%, which is almost like two-thirds, focused on a single technological approach. So, researchers are building sophisticated VR systems or intelligent chatbots or adaptive algorithms, but rarely combining them. We have these ingredients for a transformative training system, but we are cooking them in separate kitchens. So the clinical safety risks, that would be the second one. Here's a statistic that should concern anyone in healthcare education. Around 12 to 15% of content generated by the standard LLMs, in medical context, contains factual errors. These aren't minor mistakes, right? So they include incorrect symptoms, wrong treatments, flawed disease processes. So LLM based virtual patients sound confident and natural, but without grounding in validated medical knowledge, they can teach learners incorrect information. So, especially in healthcare, that's not just an inconvenience, but it's patient safety issue, right? So that's the second thing. And coming to the knowledge gap, AI and immersive technologies are typically used independently. You might practice a procedure in VR with a scripted scenario or something as such, then separately have a conversation with an AI patient. But real clinical practice is not the same, right? So diagnosis, communication, and procedures happen simultaneously and dynamically. So that's the knowledge gap. And coming to the limited adaptability, most VR and AR systems, so around like 9 out of 11 we reviewed in the depth, rely on pre-scripted scenarios. They look impressive, they feel immersive, but they can't adapt. So if a learner makes an unexpected decision, the system can't respond intelligently. The scenario plays out the same way regardless of learner's behavior, reducing the realism of education value there. And the fifth is the assessment limitations. Current evaluation frameworks focus on a discrete competency in isolation. So, test procedural skills, assessment communications are there, but the actual clinical practices require integrating knowledge, skills, reasoning, communication, and professionalism simultaneously. So our assessment tool don't reflect this complexity. These five areas together define why we need a fundamentally different approach, not incremental improvements, but architectural integration. So let me give you the evidence base for what I have just described. We conducted a systematic review spanning from 2022 to 2026, 4 years of the most recent research. We searched SciSpace for peer-reviewed journals, Google Scholar for conference proceedings, and other latest AI preprints. Okay, From the initial 646 publications or something, we ultimately analyzed 165 relevant studies in depth, with 30 receiving detailed architectural analysis. So here's what each technology category is demonstrated. So first thing is LLM virtual patients. So around 6 studies with 247 total participants is what we came up with this numbers. Okay, the good news is 85% contextual relevance. So these systems generate responses that make sense in the conversation. The concerning news, 15% contain factual errors. So that's what we observed across these studies, 6 studies here. So going to the second one, immersive AR VR. So 11 studies with around 438 participants. The strong results are like 40% better skill retention compared to traditional training, and 35% faster learning curves. And VR works for procedural skills. So the evidence is robust here, right? And the third one comes with graph-augmented AI. Only 2 studies in this criteria. It's an emerging area, but the results are striking, by grounding LLMs in structured knowledge paths, the researchers achieved 73% in factual errors. So this directly addresses the hallucination problem. And going to the adaptive learning, I think it was 5 studies with 280-ish participants. Personalized pacing reduced time to complexity by 30%. Systems that adapt to individual learner need significantly outperform one size fits all approach. And the last one, performance evaluation. 4 studies with around like 170-ish participants. So that's the AI-based assessment, which achieved 78% agreement with expert human raters for communication skill evaluation. Automated assessment is becoming viable, right? So now look, if you look at the bottom of the slide, there's still a critical integration gap. Despite all this promising individual technology, only 7% of studies integrated 3 or more complementary technologies. So 7%, it's just 7%, right? So we are in a integration paradox, I would say. So each component works, but almost no one is combining them. That's the gap our framework addresses. So going to the next slide. So now let's talk about one of the most powerful shifts enabled by AI, moving from endpoint evaluation to continuous micro assessment. So what do we mean by continuous micro assessment here? So using temporal AI models, we can track skill development constantly and consistently, not just at a significant checkpoints or something. So the system identifies uh, when is skill acquisition happening rapidly, when has the learner plateaued, uh, when are previously acquired skills starting to decay. So this would help with immediate correction, right? Immediate correction prevents the reinforcement of incorrect behaviors. Instead of practicing a mistake 100 times before discovering it on the final exam, learners receive the guidance while the error is fresh, while correction is still neurologically easy, right? So that's what we meant by immediate correction here. And coming to the granular insights, these replace generic pass fail scores. Rather than you have failed the communication assessment, the system can say your empathetic responses decreased when patients became emotional, or you rush through information gathering in the third minute. So it is very descriptive there. So, and we also observed 73% decrease in failures comes from predictive modeling, identifying at-risk learners early and intervening before they fail. So is one of our main goals here, right? So in one study with 94 nursing students, predictive models achieved 82% accuracy in identifying who would struggle. The intervention group saw dramatic failure reduction, and 78% expert agreement rate demonstrated that AI assessment isn't just faster, it's reliable enough to supplement human evaluation. So the fundamental insight we got is feedback works best when it is immediate, specific, and continuous. So AI makes this possible at scale, is what we have discovered there. So so our framework generally adapts across 5 dimensions simultaneously. One is like scenario, one, the other one is difficulty level, feedback depth, environment pressure, remediation. So now, if you look at the outcomes using these five dimensions that we are working in, 20-30% reduction in time to competency is what we have observed. Because personalized learning isn't just nicer, it's faster. Learners reach the same competency level significantly sooner. And the second one is like 73% decrease in failure rates through predictive modeling and early intervention. The study with 67 medical students showed that adaptive tutoring using reinforcement learning achieved 18% greater improvement in clinical reasoning compared to other static materials. So, and the third one, and the equity finding at the bottom, lower performing students benefited most, suggesting personalized training reduces performance disparities. Adaptive learning isn't just about optimization for top performance. Its greatest impact is supporting struggling learners. The traditional one size fits all approach failed. So the third compatibility or capability that we would like to discuss about here is immersive technology, VR and AR, which enables something traditional education cannot. Experiential learning for high stakes situations you can't safely practice in real world, right? So I'll give you evidence here, right? Across 11 studies with 400 plus participants, like I mentioned earlier, we have seen like 20 to 25 to 40% better retention, that 20 to 35% faster learning, 15 to 45% fewer errors. Now, look at the implementation modules on the right. We have this haptic feedback system, AR, and anatomical visualization and team-based simulations. So the evidence for VR, AR is robust. The limitation isn't the technology effectiveness, it's the most systems are static, prescripted, and unable to respond intelligently. That's where integration with AI becomes essential here. Now, we come to what I consider the most safety critical component, graph-augmented LLMs. So the biggest problem, hallucination. I mentioned earlier that 12 to 15% of standard LLM medical content contains factual errors. So I'll explain why. LLMs are trained on statistical patterns in language, right? So they learn what words typically follow the other words. They don't have a model of medical truth. They have a model of medical sounding knowledge, sounding language. So they cannot generate text that sounds completely authoritative while being medically incorrect. So the solution, graph constraints, so RAG, paired with structural medical knowledge graphs. Here's why I think it works. It queries validated medical knowledge graphs like SNOMED CT, and also it retrieves the relevant subgraphs. It constrains the LLM generation to be consistent with validated knowledge. And the output is clinically accurate, not just clinically plausible. So if you look at the numbers, 73% reduction in factual errors compared to standalone LLM generation. This comes from a MedCT study, which built a clinical terminology graph with over 400K medical terms and 2 million relationship. So the multi-agent architecture separates these responsibilities. And the multi-agents that we have here are patient agent, clinical knowledge agent, scenario agent, and evaluation agent. So by separating these functions, we have natural conversation and clinical accuracy. So the code at the bottom captures it. By grounding generative AI in structured knowledge graphs, we transform probabilistic language models into clinically reliable simulation engines. So coming to the next slide, now let's address the integration paradox directly. So at the left panel, if you see the integration paradox, 67% of the research focuses on single techniques and only 7% integrate three or more technologies together. But when researchers try to integrate these, the results are striking. Let me walk you through three case studies for our review. So the CLI VR is AI-powered conversational patients placed inside VR environments. The result is high engagement and realistic clinical scores. So nurse practitioner training. VR simulation combined with LLM dialogue for primary care training, patient histories, physical exams, etc., has resulted in 26% accuracy in clinical assessment. And the third one, graph augmented AI knowledge graphs combined with LLM resulted in 73% reduction in errors in factual hallucination. The value proposition at the bottom summarizes it, right? So, integrated systems provide greater clinical safety, realism, and multidimensional assessment capabilities than any single technology alone. So now let me present you the architecture solution. Four components designed to work together in a closed loop system. If you notice the circular arrow at the center, this represents bidirectional data flow. These aren't four separate modules that happen to coexist. They are designed for continuous communication. First component being the graph augmented LLM engine, which has all the medical knowledge, RAG generation constraints, and multi agent architecture. This addresses the gap of 12 to 15% factual errors. Coming to the second component, which is immersive interface layer, which consists of all the AR, VR, multimodal interaction, and real time interaction capture. The gap being addressed in this component is it adds intelligence to pre-scripted VR scenarios instead of static playback. The third one is adaptive learning module. So this is this is the guide personalizing the journey, right? So multi-dimensional personalization across scenarios, comprehensive learner modeling, and dynamic scenario orchestration. So what we are trying to address the gap here is it moves beyond single variable difficulty adjustment to comprehensive personalization based on the scenario there. And last but not least, the final component, performance evaluation system. So it provides continuous assessment. So the dimensions we talk here are knowledge, procedural skills, clinical reasoning, communication, and professionalism. Continuous microassessment versus endpoint only testing is what the main goal here is. And what the gap is that is being addressed in this component is it provides holistic view versus discrete endpoint assessment. So now a framework this comprehensive might seem overwhelming to implement. That's why modularity is a core design principle we came up with. You don't have to build everything at once. Each stage provides independent educational value. Like the stage one is clinically grounded dialogue. Second one is immersive interaction. Third one, adaptive personalization. Fourth one is complete evaluation. The scalability note is very important at the bottom. Cloud-based infrastructure and consumer-grade hardware makes this cost-effective. We are not only talking about 50K simulators. We are talking about $1,000 VR setups that match those outcomes. So I want to completely be transparent about the state of evidence, right? So this slide distinguishes between what we know versus what we hypothesize. So validated components, which are the wins in my perspective, are the VR AR effectiveness. So that gives us 40% retention improvement. The graph augmented accuracy that reduces the errors by 73%, and adaptive efficiency, which is 30% faster. But there are still some unknowns, unanswered questions that talks about integration synergy, long-term retention, and real-world transfer. So this is not a solved problem, I would say. This is a research-informed framework that addresses known gaps, and we are transparent about what still needs validation. That intellectual honesty is essential for responsible AI deployment, right? So, yep. So this is our path moving forward. Three phase roadmap where it takes at least 1 year for actual developing an actual proof of concept, and for systematic integration it could take anywhere from 1 to 2 years, and the standardization of this POC would be taking around a little over 2 years. This is what we anticipate here. So thank you for your attention today. To summarize, we have discussed about or reviewed about 165 studies and a found paradox about it. And we discussed about the framework that I have presented addresses 5 critical gaps. And the components are validated. The integration is hypothesized but research informed. So the path forward requires proof of concept implementation, rigorous trails, and honest assessment of what works. I'm very interested in collaboration with researchers who want to validate these approaches, with institutions interested in pilot implementation, with AI engineers working on related problems, and with clinicians who can ensure educational relevance. So my email is on the screen. I'm happy to take questions now, and feel free to connect with me on LinkedIn. Thank you.
Yeah, so Sriharsha, great talk. I think you got really deep into the technical aspects of the architecture and stuff. But I actually myself have a question about your talk. So I was
Yeah.
wondering for your LLMs architecture, what type of architecture did you use for that? Did you use LSTM, CNN, or like just standard transformer based
Yeah,
architecture?
it's a standard transformer based one.
Oh, okay, okay.
Yes.
And can you tell
We are
me
still
like some of the
evaluating on the best practices to get the proper outputs, but like I mentioned, we are still validating the best approaches and best models to best
yeah,
technical architecture to put into these LLMs there.
yeah,
So that's where the POC takes like 1 year. We just want to
yeah,
do it
exactly.
right. Yeah.
There is always an opportunity to contribute to the discussions that we have at EnviroCast Geo. If you are interested in attending or even speaking at a future conference, learn more at geo.envirocast.org. We're excited to hear your insights.